In this video, we are going to discuss one important outcome of both BFS and DFS called predecessor subgraph. Before moving on, let me introduce you to three more new terms. In a graph, if vertex V is discovered by exploring U vertex adjacency list, then we call U is predecessor of V. For example, for this graph, B is predecessor of F. And we can say that G is predecessor of H because we know that H is going to be discovered by exploring G's adjacency list. If U vertex is on the simple path in the tree from root to vertex V, then U is an ancestor of V and V is a descendant of U. For example, for this graph, we can say that B is the ancestor of H because if we start our BFS call with B vertex, so B is going to be our root vertex, so it is going to be an ancestor for all other vertices in this graph. Therefore, we can say B is the ancestor of H, or B is the ancestor of E, or B is the ancestor of F. And also we can say that F is the ancestor of H because we know that in the path to B to H, we have F vertex. Now, we discussed that G is a predecessor of H. Also, we can consider G as an ancestor as well. On the other hand, we can say that H is a descendant of G, or H is a descendant of F, or G is a descendant of B. Likewise. So, with those terms in our bag, let's move on to discuss about predecessor subgraphs. Now, in the breadth first search implementation, if we find any unvisited adjacent vertex, then we set that vertex predecessor to the vertex which adjacency list belongs to. Now, in this slide, in the left side, we have the graph that we ran our breadth first search in our previous examples. On the right side, we have the predecessor subgraph which produced by running the breadth first search starting from the B vertex. Now this subgraph or breadth first search tree, we call it, contains only the edges which correspond to the connectivity between particular vertex and that particular vertex predecessor. Now, one thing to notice here is that if our graph has subgraphs or isolated vertices, BFS call with source vertex will not be able to reach such a vertices. In such cases, we tend to run BFS with multiple sources, which will result in more trees in our predecessor subgraph. Even though conceptually this scenario can happen, but in practice, we usually use breadth first search as subroutine where our vertex in graph can be reached from the source vertex. So this scenario almost will not happen in the applications. But for the depth first search, this is a bit different because depth first search we used commonly as subroutine for other algorithms. Now, in order to traverse to all the vertices in a graph with DFS, we most likely to make multiple DFS calls with different source vertices, and such a multiple calls will result in predecessor subgraph known as depth first forest, which will have multiple trees. For example, let's consider this graph. If we start our DFS with vertex 3, then the vertex 4, 7 and 8 will not be visited because there is no path to reach such vertex from the vertex 3. Hence, in the DFS, after initial call returns, we will iterate through our vertex list and we will call DFS again on unvisited vertices in our vertex list. So, if we run our DFS algorithm this way, one possible outcome or one possible predecessor subgraph which is generated from this DFS call will be look like as follows. Note here we have two trees. Hence we are referring this kind of predecessor subgraph as depth first forest. Now let me introduce you to a way which will printing out the graph while we traversing through DFS, which will emphasize the structure of predecessor subgraph or which will emphasize the different trees in the predecessor subgraph. So in our depth first search call implementation, we are going to make a small change. Now here, as soon as we start our depth search call, we are going to print out the open parentheses and the particular node's ID. And at the end of this function, we are going to printing out this particular vertex node ID and with the close in parentheses. This change will print out our graph in a particular way, so we can clearly identify the trees in the particular predecessor subgraph and the ancestor and descendant relationships. Now this outcome corresponds to a scenario which we use the previously discussed graph and we given the start vertex as 3. So let's see how we can interpret this outcome. For that we are going to use two simple rules. The rule number 1 is, if interval u and interval v are entirely disjoint, then neither v nor u is descendant of other in depth first forest. For example, the set start with the 3 and end with the 3 is disjoint from set start with 4 and end with 4. So we can guarantee that neither 4 and u are descendant of each other. The second simple rule is that if the interval v is contained entirely within interval u, then v is descendant of u. For example, set start with 7 and end with 7 is entirely within set start with 4 and end with 4. So we can deduce that 7 or node 7 is descendant of node 4 in this depth first search call. In same way we can deduce that node 5, node 6, node 1, node 2, they all are descendant of node 3 because they all are inside the set start with 3 and end with 3. So if we use previously discussed rule, we can end up with something like this or trees like this. Now here we have two distinct set of parentheses enclosed with 3 and 4 as we discussed before. Therefore we are going to have two trees here. For the first tree, all the vertices are descendant of 3 because all other vertices inside the vertex 3 or set start and end with 3. Therefore we can conclude that node 2, node 1, node 5, node 6 all are descendant of 3, which means in this tree 3 will be our root vertex. And also notice that node 1, 5 and 6 all are enclosed by node 2 or set start with 2. Therefore we can conclude that node 3 has only one direct descendant and all other nodes are descendant of 2. Now inside set 2 we have two disjoint sets enclosed with 1 and 6. Therefore we can conclude that node 2 has two direct descendants, which is 1 and 6. And inside set start and end with 1 we have node 5. Therefore we can deduce that node 5 is a descendant of node 1. In this way we can build the other tree as well. Now that's it for this video. In the next video we are going to discuss more about predecessor subgraph and usage of predecessor subgraph as well. Thank you.